So you guys are going to start by answering these questions. So you can have a chat with your neighbors about that. I'm going to draw some cards today, so if you don't know the answers to any of them, go and find someone who does. Okay? There they are. You guys need a little more time? Yes. You need scrap paper? You got some? There's no here right there. So many people away. Crazy. Do you guys need a minute more? Or are you done? Anyone done? Okay. Who needs a minute more? Nobody. Oh, one. Okay. I'll give you another couple minutes. And if you're done that and you would like to try, what is the oxidation number of chromium in CrC2O4? You can try that one. Okay, let's do this. What is oxidation, Sylvia? Sorry? The electrons are in the products. Yes, that is true. That is true. What is a definition, though? Katie? The loss of electrons. Because you won't always be able to see the electrons in the products if you have an overall reaction. If you have a half reaction, you'll be able to see them, and we'll take a look at that today, what the difference is between an overall and a half reaction. So oxidation is losing electrons. And if you needed to remember that, is there a little mnemonic device you can use? What is it? Leo. Leo the lion says, grr. All right, so what is the definition of reduction, Stephen? Yep, gaining electrons. All right, this one's a little trickier. What is an oxidizing agent? Dylan? That's okay. You don't need to know yet. You're learning, right? Mm-hmm. Joanne, what is an oxidizing agent? It's the thing that gains the electrons, yes. So it gains the electrons. Which means that it is oxidized or reduced? Reduced. If it is reduced, then why do we call it the oxidizing agent? Yeah? Yeah, it's oxidizing the other thing. Yeah? So it oxidizes the other element, the one that is undergoing oxidation. And how does it do it? It rips electrons off it, right? And that's how it gains its electrons. What is a reducing agent, Aditya? It's the one that's accepting the electrons. Yeah, is that true? If it accepts the electrons, that would mean it's gaining electrons. It's giving electrons. It's the one that gives electrons to the other guy. And in giving the electrons to the other guy, I should say the other species. That would be a better word. Why don't I change that to species? You can use guy if you want to. This reduces the other species. Good God, why can't I write? So have you guys heard of a casting agent? Like in Hollywood? What do the casting agents do? They go around and they pick actors and they get them cast in movies, right? So who's getting cast? Is it the The casting agent who's getting cast in the movie? No, they may end up getting the other person cast. Yes? So the oxidizing agent oxidizes the other guy. The reducing agent reduces the other guy. So what happens to the oxidizing agent is the reverse. The oxidizing agent gets reduced. The reducing agent gets oxidized. Little bit confusing, but if you think about it, it's okay. All right, find the oxidation number of carbon in C5H10O. How do we do that, Harshika? We end up with -8/5. Do you guys agree with her? Yeah? Okay, just in case anyone has forgotten how to do this, or if you get in trouble with some of the later ones, how I would do this, writing it all out, is I would say I have 5 carbons, 10 hydrogen, and 1 oxygen, and my overall charge is 0. Carbon is my unknown, so I leave it there. The oxidation number of hydrogen is how much? +1. The oxidation number of oxygen is how much? -2. And equals 0. So now I have 5 carbon, and then I have +10 and -2 is +8 equals 0. So I end up with 5 carbon is equal to -8, and that takes us to carbon is equal to -8/5. Okay, excellent. What is the oxidation number of chromium in C2O4? Anyone having any difficulties with that one? Because maybe we're like, I don't know the oxidation number of carbon. How am I supposed to find chromium if I don't know carbon? Yeah? Okay. Here's the trick. You don't need to know the oxidation number of carbon, because do you know the charge of C2O4? Yes, it is what? And how do I know that? Because it is on the data booklet. It's the oxalate ion. Oxalate? Oxalate is C2O4 2-. And if C2O4 is 2-, what's the charge of chromium? 2+. And therefore the oxidation number of chromium is 2+. So similarly, what would be the oxidation number of lead in lead sulfate? You don't know the oxidation number of sulfur, but you don't need to. What is the oxidation number of lead in lead sulfate? 4+. Why? Because you got 2 SO4s. They are 2- and 2-. So you can use polyatomic ions. You can just use the whole charge of the polyatomic ion. Okay, and I bring this one up because it doesn't actually come up that often, and people sort of get stuck on it, even though this is something you've been doing since grade 9, right? Figuring out the charge of the multivalent metal. So if you have a multivalent metal and it's with a polyatomic ion, just find the charge of the polyatomic ion, and boom, that'll help you find the charge or the oxidation number of your metal. All right, try that one. If you can consistently do these in your head, you're better than me. I like to write them out. Whoops. So what do we put in for oxygen? -2. What do we put in for chlorine? -1. And what do we put in for fluorine? -1. So we have sulfur, and then we have -4 -6 is equal to 0. Is that a correct answer? Yes, sorry. No. Oxygen is never peroxide unless it is peroxide. Okay? If you are using oxygen to find something else, it is never peroxide. Okay? The only time it's peroxide is if you have a metal and oxygen. Yeah? Or hydrogen and oxygen, but it's not water. Okay, so never peroxide if you're using oxygen to find the other thing. Okay, in this case, you would be using sodium to find the oxidation number in oxygen. Yeah? Good question. Are we happy with this answer? S equals 6. No, why not? Every oxidation number needs a charge. So if it's positive, you have to write the positive. This positive is required. Okay, let's try the U in Mg U2O7. I guess it's kind of like a Cr2O7, I guess. What's the oxidation number of magnesium? Yeah, in a compound, it's +2. Oxygen is -2. And so we have what? -14, and 2 is -12. So we have 2U is equal to +12, and then U is equal to +6. Is good? Okay. Do we have any others? C in C4, H4O4, 2-. This is our last one. +1/2. Excellent. Do you guys feel fairly confident with this? Okay, if you feel like you need any practice on this, this is on page 7. Okay, so if you're like, I just need a little brush up on it at some point, that is on page 7. Okay. Yes. Yeah. Diuranate. So it's kind of like dichromate. It's ionic with a polyatomic ion. It's Mg, 2 plus. And instead of Cr2O7, we have U2O7, 2 minus. They are analogous. So you could, like, let's say we had just U2O7, 2 minus, we would have 2U plus 7O is negative 2. 2U minus 14 equals negative 2. 2U is equal to positive 12. And we're back where we were with the magnesium. So it doesn't really matter if the magnesium is there or not. You'll end up with the same result. Okay? Yeah. All right. And now we are going to go to 6.1F, which is balancing half cell reactions on page 18. No, we're not. I lied. Lying. 6.1D on page 10. Sorry, got ahead of myself. So, did Tyler teach you the term redox reaction? Yeah. So a redox reaction is a reaction where we have two processes. We have both reduction, which is the read, and oxidation. But strangely enough, if we are talking, if we use like the full words, we don't call it a reduction oxidation reaction. We call it an oxidation reduction reaction. But I guess oxred didn't sound as good as redox. And it involves the transfer of electrons from one species to a second species. And we can actually separate a redox reaction into two half reactions. Okay, so instead of having an oxidation reduction reaction, we'll have an oxidation half reaction and a reduction half reaction. So 1/2 of that is the oxidation half reaction, which you'll often see written as a half reaction. And the reduction half reaction is there. What is happening if we have oxidation? Remind me. Oxidation is losing electrons. So if we go over and we look at this oxidation half reaction, the electrons are in the products because they're being lost. Reduction is gaining electrons. And you can see that the electrons are gained. In other words, they are in the reactants and they go in. So that is one way that you can tell if a half reaction is an oxidation half reaction or a reduction half reaction, is by where the electrons are. So if the electrons are in the products, you have oxidation. If electrons are in the reactants, you have reduction. But there's another way as well. What is the oxidation number of sodium on the left? This sodium here. Everybody should be able to tell me this. It is negative? Does it say negative? It doesn't say negative. It is 0. Any element on its own is 0. What is the oxidation number of sodium on the right-hand side? It is +1. Okay, so as we go from 0 to +1, what happened to the oxidation number? The oxidation number got bigger, higher, okay? And if the oxidation number gets bigger, that is oxidation. Does that kind of make sense? The oxidation number gets bigger, it is more oxidized. Yeah? The other one makes even more sense, because let's look at what happens in our other half reaction. We have our oxidation number of chlorine. What is our oxidation number of chlorine on the left? Cl2. 0, because it's an element on its own. Okay? What is the oxidation number of chlorine on the right-hand side? -1, because that's what it says. Okay? So it went from 0 to -1. So we went from an oxidation number of 0 to an oxidation number of -1. So that number got smaller. The oxidation number got smaller. What's another way of saying smaller, got smaller? It got reduced, literally. So what is being reduced in a reduction? The oxidation number is being reduced in a reduction. Okay, so this is just a summary. If you have the electrons in the products, that is oxidation. If you have the electrons in the reactants, that is reduction. So here are our electrons in the reactants. Here's our electrons in the products. Is good? Okay. Now, in nature, do these half reactions actually exist in isolation? Is it possible for someone to be gaining electrons without somebody else losing them? Is that possible? No. Okay? So this whole half reaction business is kind of, it's like an intellectual exercise, a little bit. Okay? But it becomes very, very handy when you are balancing redox reactions and when you're looking at electrochemical cells, because you physically separate the two half reactions and you connect them with a wire. Okay, so although both need to be present, you'll have a half reaction over here. It'll be attached by a wire to a half reaction over here, and there'll be another wire or actually some solution forming the circuit, completing the circuit. And we'll look at that a little bit later. But for now, you should just realize that half reactions never exist in isolation from each other, okay? One thing has to be getting oxidized, the other thing has to be getting reduced. All right, so let us get you guys to recognize from these three reactions, A, B, and C, which is an oxidation or a reduction. Once you've done that, check with your partner. I'm going to call some more names. Are we ready? What is A, Ansel? Oxidation. Not oxidization, oxidation. No zation, just dation. Zation, dation. Yeah. Oxidation. What is the second one, John? Reduction. And the third one, Victoria. Oxidation, yes. And you can tell that because of where the electrons are. How else could you tell? What if the electrons weren't there yet? We can look at the charges. We can say, here, the oxidation number got bigger. And therefore it is oxidation. Here we went from +2 to 0. The oxidation number got smaller. Therefore that was reduction. And in the last one, you would have to do a little more work on this one because you don't have like lovely charges just sitting on the element. You could look at I2 and say, what is the oxidation number of I2? 0. What is the oxidation number of I in IO3 minus? Did you guys get +5? Excellent. So it went from 0 to +5. And don't just totally ignore the coefficients. They have nothing to do with it, okay? It's just you're looking at the single species. It went from 0 to +5. It got bigger. So that is oxidation. Okay. So we have A is a plane, is a very simple oxidation. B is a very simple reduction. And then you'll notice that C gets more complicated. Yes? Fairly soon, like on the next page, we're going to look at balancing the charge in half reactions. Because just like you can't have atoms appearing out of nowhere or disappearing, matter has to be conserved, charge also has to be conserved. So whatever your overall charge is in the reactants, it has to be the same as the overall charge in the product. So if we look at the first one in A, we have 2 negative on the left. We have 3 positive on the right, but we also have -1. So what is the total charge on the right-hand side? 2 positive. Is that what it was on the left-hand side? Yes. So that is balanced in terms of charge. That's how we know we have the right number of electrons, okay, is that it makes the chart, they make the charges equal. Over here we have a 0 charge. Here we have a 2+ charge and a 2- charge. So what is the overall charge on the left? 0. Is that what we wanted? Yes. So you can imagine if I gave you an Fe2+ and Fe0, you would know where to put the electrons, yeah? What if I just gave you I2 goes to IO3- and I said balance that sucker? You'd be like, huh? And you wouldn't know. You'd be like, I don't know. Where'd you get those 6 water from? Where'd you get those 12 hydrogen from? I don't know what's happening. But don't worry, we're going to get to that later. Okay? Later today. It's very easy. You'll like it. There's steps. Okay. Half reactions are important for balancing redox equations and for determining the voltage of electrochemical cells. We will get to both those topics later, one of them later today. For now, we're only going to identify and write some simple redox reactions. So how do we get the half reactions out of an overall redox reaction? Well, we start by writing the net ionic equation. Once you have the net ionic equation, you separate it into 2 half reactions. And then finally, for these very, very simple ones, all we are going to do is we are then going to add electrons to balance the charge. Just like we were talking about, we need the overall charge on both sides to be the same. Overall charge in reactants, same as overall charge in products. Okie dokie. We are not going to do a demonstration of this because today's a short day. I might haul it out tomorrow. But what you can do is you can take, if you want to, you can go watch this video at home. But what you would do is you would take some aluminum and you would throw it into some copper 2 chloride solution. All right. And then we would end up with aluminum chloride and copper solid. So this beaker here has had some of the copper. This used to be a solution, like a blue solution of copper 2. I threw some aluminum in there. I usually have one of these going because we usually have some waste. I like to get rid of the copper 2 because it's bad for the fishies. Okay, and so we react it and we end up with aluminum instead of copper. And we get, this one I actually collected from one of those reactants. What's that look like? It looks brown. And that came from that reaction. Can you guess what it is? It is copper. Why don't you guys pass that around? Make sure everybody gets a chance to see it. Now let's take a look at our oxidation numbers here. What is the oxidation number of aluminum on the left? Aluminum is 0. What is aluminum on the right? 3+. So what happened to aluminum? It got oxidized. The oxidation number increased, therefore Al was oxidized. The only way for an oxidation number to increase is for it to lose electrons and become more positive. All right, how about copper. What is the oxidation number for copper on the left? 2 plus. And on the right? 0. And so the oxidation number went down, and therefore copper was reduced. Now, how about chloride? What's the oxidation number of chloride on the left? -1. What's the oxidation number of chloride on the right? -1. So that means that chloride was not involved in the reaction. It is just a spectator ion. So to write the half reactions in here, first thing we need to do is write the net ionic equation. You can go straight to the net ionic equation if you can see that the chlorides are the spectator ions, or you can go through the complete ionic equation, the CIE. Where we split apart the copper chloride into 3 Cu2 plus and 6 Cl minus. And we split apart the aluminum into 2 Al3 plus and 6 Cl minus. And then from there, we would cross out our spectator ions. But like I said, that's not necessary. If you can go straight to the net ionic equation, go for it. Okay, so here is our net ionic equation. And then you take the two species that are the same, so aluminum pairs with aluminum and copper pairs with copper, and you separate those out. So you end up with all the aluminum over here, and you end up with all of the copper in a separate half reaction. So this is now our half reaction. Half reaction. And together they make the full reaction. Okay. Now, because we have coefficients where we have a 2 and a 2, and we have a 3 and a 3, what should we do with those coefficients? Reduce them. Okay, so we'll just end up with Al goes to Al3 plus, Cu goes to Cu. And at that point, you can say that aluminum has been oxidized. Ooh, is it the oxidizing agent or the reducing agent? Al is the reducing agent. Copper, on the other hand, went from positive to 0. So copper copper has been reduced. Oh, I should say oxidized. That's terrible grammar. Aluminum has been oxidizing. Ooh. Reduced. Cu is the oxidizing agent. In order to make the charge equal on both sides, would we add electrons in the aluminum reaction? Would we add electrons to the left or to the right? We would have to add them to the right because you can only bring a more positive charge down. You cannot by adding electrons. So yeah, we have to add the electrons over here. How many? 3. And where would we put the electrons in the copper reaction? they would have to go on the reactant side. And how many? 2. That gives us a 0 overall charge on the left and a 0 overall charge on the right. Is good? Okay. This just walks you through the whole thing. Let's go to the little notes on the next page. Note number 1. The overall charge on each side has to be balanced, but it does not have to equal 0. That example we did, it equaled 0. It does not have to equal 0. So for example, we might have Fe2 plus becoming Fe3 plus, yes? And we would need to have 1 electron over on the right-hand side to bring that charge on the right down to 2 plus. The charge on the overall charge over here is +2. The overall charge over here is +2. So they are equal, but they are not equal to 0. Okay? Second note. Oh, this is just what we already did. I guess I gave away the punchline. But you can tell if a half reaction is oxidation or reaction because if the change in oxidation number, and you'll see this notation fairly often, this is our change in oxidation number, delta ON. That saves you some writing. If the change in oxidation number is positive, it is oxidation. Okay. In other words, if the oxidation number gets bigger. If the change in oxidation is negative, in other words, if the oxidation number gets smaller, we've had reduction. Okay. Do you guys think you could take this reaction, cover up what's down below? Could you find the 2 half reactions and balance them? If you do it the long way, you can write your complete ionic equation, your CIE. Whoops. Splitting apart the aqueous KCl and KF. And then you can say, oh, who's my spectator ion? My spectator ion is the, okay. And then from there, you can put the F with the F, and you put the Cl with the Cl. There's our F with our F, our Cl with our Cl, and you can hopefully see where would I need to put the electrons for the fluoride. Products or reactants? Reactants, because I've already got 2 negative over here, so we would need to have 2 electrons here. Over on the right, we have 2 negative on the left, so we would need to add 2 electrons to make it 2 negative on the right. Is good? Okay, excellent. So we now have our reduction half reactions. This one, the electrons are in the reactants, they're being added in, they're gaining electrons. And over here we are losing electrons. Okay, and that's it for that. And now we're going to go to page 18. Yep. This is not an exciting video, this one. This is just me teaching it some other year. There was some year when I had to, I forget what happened. It was during COVID. And for some reason or other, we were short on time. Like we did not have as many weeks or days or hours or whatever the heck it was. So I made them learn electrochem on their own. Sort of like before. I think we were in, maybe we were in quarter 2, so they had to learn it in quarter 1. I can't remember, but it was not a fun year, whatever happened. So rules for balancing half reactions. And this is going to help us with reactions like, I don't know if you remember, we had that I2 going to IO3 minus. That's our skeleton half reaction. And you can't just balance that by adding electrons, right? Like that would not solve your problems. So we need a different method for solving more complicated half reactions. So we are going to use the little mnemonic, major hydroxide OH says charge. Okay, so major hydroxide says charge. So what we are doing is we are balancing the major atoms. What the heck are the major atoms? The major atoms are all elements. Oop, meant to make that yellow. They are all the elements except hydrogen and oxygen. And to do that, we balance them the normal way that we would always do it by adding coefficients. The second element that we balance is oxygen, and we don't do it the normal way. We don't add coefficients. Instead, we just throw in water molecules. So if I had 5 oxygens on the right and none on the left, I would add 5 waters to the right to give me the correct amount of oxygens. Okay, so we balance our oxygen by adding H2O. But in adding H2O, we're throwing hydrogens in there willy-nilly. Yes? So hydrogen's going to be all out of whack. So we need a way to balance the hydrogens. And we do that by making the solution acidic and adding H plus ions. Okay, so H atoms, we sort those out by adding H plus ions. And then finally, we do what we were just doing a moment ago, and we balance the charge by adding electrons. And the other class said that they would like these rules printed out so that they have it just for reference. Okay, so I'm going to do that for you along with balancing full reactions, because these four steps are fairly straightforward, and they will get you a reaction that is balanced in acidic conditions, because you had that H plus in there, or if you didn't have to add any H plus, it would be in neutral conditions. Okay? However, sometimes you don't want it to be in acidic conditions, you want it to be in basic conditions. And I don't even know that going through these steps not in context is helpful, but basically what you do is you neutralize the hydrogens by adding hydroxide. Okay? That's the major thing about it. You just neutralize whatever hydrogen atoms there are by adding hydroxides. And if you had 3 hydrogen ions, you would add 3 hydroxide ions. And you do that to one side of the equation. You also have to do it to the other side of equation because otherwise you've unbalanced things. And then instead of having H and OH, you make water. Cancel anything that needs canceling. Steps 5, 6, and 7 will make a lot more sense in an example. Okay? But like I said, I will have these rules printed out for you on a separate sheet of paper so you can just have it like as a reference if you need it. But for now, we're going to do one that is just in acidic conditions. This is a half reaction. And which element is undergoing oxidation or reduction? Which one is either gaining or losing electrons? There's only 2 choices. There's manganese and oxygen. Manganese, okay? I'm going to give you guys a little hint that I forgot to give the other class. If you throw oxygens onto something, what do you think you've done to it? I have added oxygens on. What do you think I've done? Have I oxidized it or reduced it? I have oxidized it. So if you have a substance, I could just look at this and say, that was oxidation, without finding oxidation numbers, without balancing the reaction. I can just look at it and go, oh, there were no oxygens, now there's oxygens. Now I'm choking on my salad. Sorry about that. This is oxidation. Okay. Let us balance it though. And what are the 4 steps that we use? We have major. What comes after major? O, and then H, and then charge. And major just means anything that is any element which is not O or H. So who is the element that is not O or H? Manganese. Does manganese need balancing? No, we have one. And in fact, most people, well, a lot of people will forget step 1 because very often we don't use step 1 because very often you've got a 1 and a 1. So don't forget to check for step 1, okay? Don't forget to check. So we got our major element there. It's already done. How do we balance oxygen? Oxygen, we add water. So what we're going to do is we're going to rewrite our equation down here. Which side will we need to add water to? We'll need to add it to the left side. So we have Mn3 plus how many water? 4. So we have now balanced oxygen. Next, we need to balance hydrogen. How do we balance hydrogen? What do we add? H plus. How many H pluses do we need to add and to which side? We need to add 4 times 2 is 8 hydrogens, and we need to add them over here. Now, many of you will be able to do this in your head, but I will also say that many people also make errors when it comes to finding the overall charge, okay? So what I like to do is I like to find the charges and write them down on the side. So over on my left, I'm going to say I've just got a 3+ here. So I'm going to write 3+ and I'm going to put it in a little circle. That way I know I've got 3+ in my reactants. In my products, I've got a -1 and I've got a +8. And when I add those two together, I get +7. So do I add electrons to the side that is more positive or less positive? Yeah, we add electrons to the side that is more positive. How many electrons do we need to add? We need to add 4 electrons. And that will bring our charge down to +3, which makes it the same as the other side. Okay? And that is a balanced half reaction. Now, if you didn't already know that we threw oxygens on it, so it was oxidized, could you tell from where the electrons are that it is oxidized? Yes. Could you tell, what's the other way you could tell that it's oxidized? You could look at the oxidation number of magnesium. So, to tell if an unbalanced half reaction is oxidation or reduction, you can either one, you can balance the half reaction and see where the electrons are. If the electrons are in the reactants, that would be reduction. If the electrons are in the products, that would be oxidation. Or you can find the oxidation number. And if the oxidation number increases, that's oxidation. If the oxidation number decreases, that is reduction. Or if you threw a lot of oxygens onto it, it's oxidations. If you took oxygens off of it, it is reductions. That's not always going to be the case, though. Sometimes you have to actually look at the oxidation number because it becomes a little bit because there's also hydrogens. If you put hydrogens on, that's reduction. If you take hydrogens off, that's oxidation. This is really useful for biology. Okay, take hydrogens off, that's oxidation. Put hydrogens on, take hydrogens off, oxidation, on, reduction. This is not a surefire method. But if you're in a hurry and you're doing a multiple choice question, bam. You know, you kind of go with it. Okay. Shall we do one more example? Okay. Fruit fly. Oh, look. It's the one we were talking about before. We've got I2 goes to IO3 minus. So we want major OH charge. So what do we do? Are our major elements, who is the major element here? Iodine. Is the major element balanced? No. What do we use to balance the major element? I was going to say element. We use coefficients. It's the one that we do just like we used to do, you know, our grade 10 balancing, grade 11 balancing. So we put a 2 here. Okay. How do we deal with oxygen? We add H2O. How many oxygens do we have on the right-hand side? 2 times 3 is 6. Absolutely. So we have 6 oxygens. So how many water do we need to add? 6. Hydrogens. How do we deal with hydrogens? We add H plus ions. This is going to make it acidic. Okay, how many hydrogens do we have? We have 6 times 2 is 12 hydrogens. So that means on the right-hand side, we need to add 12 hydrogens. And now we're going to do our charge. Keep track on the sides. What is the overall charge on the left side of the equation? 0. There's nothing that's got a charge over there. So that's 0. And on the right-hand side, how much negative do we have? 2 negative, and how much positive? 12 positive. That gives us a total of 10 positive. So to which side will we add electrons? To the right side. How many will we add? 10. Is good, is easy? Okay. Excellent. We'll leave it there for today. Your homework is pages, is it 13, 14, 15, I think? Let me double check on that. I think it is. Yep, 13, 14, 15.